Hi class, welcome to this screencast about average rates of change, AROCs, and instantaneous rates of change, IROCs. Remember that the instantaneous rate of change is the same as the derivative, so we're going to be using that language for both things, instantaneous rate of change and the derivative, the same. So I want to do it through this particular problem. So in this problem, a ball is thrown straight up in the air from a height of 48 feet. And it's given an initial upward velocity of 8 feet per second. And then from physics, we know this function works. F of t equals negative 16t squared plus 8t plus 48 feet per second. So you're just given that. And that's going to go for the interval from 0 to 2. So if you're looking at this notation right here, remember that this notation expresses an interval. When you see those square brackets, it's an interval that includes the endpoint. So this is the interval that starts at 0 and goes all the way up until t equals 2, between 0 and 2. So the first thing that we want to do is to draw a graph of the function and use the graph to see whether the ball's heading up or down. To graph this, I put it into Google and just said graph the function and wrote out the function, and you can see the graph that I got. To see whether it's rising or falling, look at this blue dot that's right here, and you'll see that at t equal 1 second it looks like the graph is going down, so the ball is falling. Or the height is decreasing. Now the next question says find the AROC on a couple of different intervals and decide which is the better estimate of the instantaneous rate of change. So to find the AROC on the interval from 0.5 to 1, we can do the usual thing for AROCs. We're going to do the difference in output over the difference in input, otherwise known as the rise over the run. So we'll do f of 1 minus f of 0.5. That's going to be the change in the height of the ball over the time that it took, 1 minus 0.5. It took a half a second to do this. So up top, f of 1 turns out to be 40, and f of 0.5 turns out to be 48. So we have 40 minus 48, or it's gone down by 8 feet during that time. And on the bottom, we have the 1 minus 0.5, which just turns out to be 0.5. So altogether we have negative 8 divided by 0.5, which ends up being negative 16. And remember, since this is a real problem, we have units here. What are the units going to be? They're the units of the output over the units of the input, or in other words, the output is in feet, the height of the ball is in feet, the input is in seconds. So this is feet per second in terms of our units. We do a similar calculation for the interval from 0.9 to 1. In this case, we have the AROC is going to be f of 1 still, but this time minus f of 0.9. So this is the height drop in that 0.1 second that happens. And our difference in time here is going to be 1 minus 0.9. So we have a smaller interval of time, just 0.1 seconds. And these, if you find f of 1, that's of course again 40, since we already found that, and f of 0.9 turns out to be 42.24. And no, I did not calculate that in my head that fast. I had already done it before I started this screencast. And here we're dividing by 0.1 seconds. So altogether this gives us, again, it's still a fall of negative 2.24 feet over 0.1 minute. Or we've got negative 22.4, and the units are the same. It's still feet per second. That's how fast it was dropping on average during that interval. Which of these is the better estimate? The better estimate always comes from taking the smaller interval. So the best estimate that we can get is going to come from this one. The second one here gives us our best estimate. But of course we don't need to stop there, right? We could get better and better estimates And that's what part C is about. If we look at a number of different intervals, we can look at what those estimates are going to be. And it's a good idea to fill out this table yourself for practice. So I would suggest just pause the screencast here, do the rest of these that haven't been done yet, and then come back in a moment and I'll reveal what all of the answers are. Great, you're back now, aren't you? I hope you really went and did that. The first two we did together, so -16 and -22.4. From 0.99 to 1, we'd have -23.84. If we looked at that, so that's an even smaller interval. Now we flip over to an interval on the other side, from 1 to a tiny bit more than 1. That's going to give us -24.16. Then we go to -23.984. That's from an even tinier interval, just 0.0001 seconds long, that interval is, and a 0.0001 second interval on the other side gives us -24.016. So you can see, roughly speaking, the first two, right? These are relatively large intervals compared to the second two, which these are all intervals of length 0.01, right? And then the last two both have length 0.001, and we can see a general trend here, right? The intervals that go before 1, from the time before 1 all the way up to 1, are a little bit under 24. The intervals after are all a little bit over 24, and they're all getting closer and closer to 24. So that speaks to D. Can we make a guess about the instantaneous rate of change at t equal 1? I think that we could. I think that the IROC at t equal 1, I'm going to guess it's going to be -24 feet per second. And that's how fast the ball is traveling right then. Note that this is also the quantity that we call the derivative. This is f prime of 1. This is the derivative at 1 is the same as the instantaneous rate of change at 1. But the trouble is, it sure looks like that's the answer, but could some freak fluke happen and that's not the answer? That's one trouble, actually. The other trouble is, it takes a lot of time to fill out this table, and I think, as I've mentioned to you before, I'm pretty lazy and I hate doing things that take a lot of time, especially when they require repetitive work. That's where algebra comes in. That's why algebra is really useful. It can do all of these problems at once for us. So instead of thinking through a whole bunch of different little intervals, we're going to think through one interval. It's going to be the interval as t goes from 1 second to 1 plus a little bit. 1 plus h. So think of h as some kind of tiny number. And I'm going to find the AROC on this interval. Okay, so here we go, finding the AROC. The AROC is going to be equal to, just as we did before, f of the end, or the height at the end of the interval, minus f at the beginning, or the height at 1 second. And then we're going to divide that through by how long it took to do that. How long is that interval? Well, it's h long. If you don't quite see that it's h long, remember that this is length is 1 plus h minus 1. Those 1's are going to cancel, leaving just a length of h. So now I have to plug 1 plus h into my function. So scroll up, or if you look upward, you will recall that the function that we're talking about is going to be -16 times the input t squared. In this case, that t is going to be 1 plus h squared, plus 8 times our input t, and in this case the time is 1 plus h, and then we'll add 48 to that. So that's f of 1 plus h, and then I'm going to subtract off f of 1. Now you can go and calculate f of 1, but remember we did it already. It turns out that it's going to be 40. So this first part here is this long expression here, and f of 1 is just our previously calculated 40. And notice that I subtract the 40 because I'm subtracting f of 1. And the denominator of this is just going to be h. So now I have to unpack this a little bit. That'll be negative 16 times 1 plus 2h plus h squared. I suggest that you FOIL it out to check me. And I can distribute the h here. So this is h plus 8 plus 8h. Plus 48 minus 40, I think that just means plus 8. So let's see what we've got here on the bottom. We've still got h. And I gave myself a little more room to finish this problem out. Now I'm going to have negative 16 minus 32h minus 16h squared plus 8 plus 8h plus 8 more, all over h. So notice what's going to happen here. This negative 16 cancels out with these two 8s. And I can combine the negative 32h with the 8h. So I've got negative 24h now minus 16h squared all over h. And notice I can do more cancellation, at least provided that h doesn't equal 0. We can factor an h out of the top. Which would allow me to cancel the h on the top and bottom, provided at least that h isn't equal to 0. Okay, so now we have a nice tight expression for the average rate of change on this interval from 1 to 1 plus h. It's negative 24 minus 16h, provided that h isn't equal to 0. If I want to find the instantaneous rate of change, the IROC, also known as the derivative at 1, I'm going to have to look at what happens as h gets closer and closer and closer to 0. So I want to take this expression and imagine what's going to happen as h gets closer and closer to 0. Well, what's going to happen? That negative 16h that's sitting there is just going to go away, right? So eventually that, that piece at the end there is just that negative 24 minus 16h. That's just going to disappear, right? As it gets close to 0, that's going away, and we're just left with negative 24. So the instantaneous rate at which this ball is dropping at the second where the time is equal to 1 is going to be negative 24 feet per second, which is exactly what we predicted, remember. But we found it for sure and logically using algebra and without having to do a whole lot of calculations to see what the trend is. Just one kind of ugly algebra calculation, which isn't so bad maybe once you get used to it. I'll see you in class on Monday.